Alright, so let us start our next PYQ sessions. In this session, we are going to solve nest PYQs from limits and continuity. And we will start with this particular MCQ which appeared in 2007. It's a limit problem. The limit of sine inverse of x minus sine of x upon x cube as x tends to 0 is 0, 1 upon 3, 1 upon 2 and 1. Now, to solve this problem, the best approach would be L'Hospital's rule. Okay, so let us see whether L'Hospital is applicable first of all. See, in most of the cases it will be applicable because you cannot have a multiple choice question for such entrance examinations. Sorry, it seems somebody is calling. Oh, guys, excuse me, just a second. Sorry. Yeah, okay. Yeah, so first of all, we need to check whether L'Hospital's rule is applicable, and it will, in most of the cases, it will be applicable because the direct substitution of 0 here, if you see, sine inverse of 0 is 0, sine of 0 is 0, and cube of 0 is 0. So that indeed is an indeterminate form, so we can apply the L'Hospital's rule. Okay, now when we apply the rule, we differentiate the numerator and the denominator separately. We know that derivative of x cube, that would be 3x square. Derivative of sine inverse of x would be what? 1 upon root of 1 minus x square, and derivative of sine x would be cos x. Okay, now let us again see what form we get after substituting x as 0 here. Okay, well, with the denominator being 0, we know that now the numerator should be 0 because in all of the options we don't see anything like infinity or limit doesn't exist, right? And you see that here cos 0 is 1 and this x squared is 0, 1 minus 0 is 1, root 1 is 1, so that's again 0 by 0. Which means we have to apply L'Hospital's rule one more time. Okay, we have to apply L'Hospital's rule again, but well, we can apply it right here, but what I'm recommending you is first you make an adjustment here. Okay, and that adjustment is you can take this 1 upon root 1 minus x squared outside. I'll tell you the reason after we do it. Okay, so if I take this 1 minus x squared outside, not exactly outside but common from the numerator, then we will get 1 here, and here we will have 1 minus x squared into cos x, right? We'll have 1 minus x squared into cos x. Now, why did we do it? Okay, well, we have product rule here. That's first, and if at all we are going to apply the rule again. But now this part has been taken care of. Why? Because if I substitute x equal to 0 right here, I am not getting 0 in the denominator, correct? And I know from algebra of limits, what do I know? That limit as x tends to a f into g, if I want to find, I can find the limits individually as long as I know that the limit of the product exists, right? And so I'll do it here now. So for this part I will put 1, this part I'm going to put 1, and then let us apply the rule. Okay, let us apply the rule. Okay, so what is the derivative of 3x squared now? What is the derivative of 3x squared? It will be 6x. Okay, and let's now go for the derivatives here. Look, well, although we didn't check it for 0 by 0 form, it is indeed 0 by 0 because this is again anyways 1 and this is cos of 0, so that is also 1. Okay, okay, so let's go to the derivative of 1 now. That's 0, right? Now let us apply the product rule here, u dash into v. Now derivative of root is 1 upon 2 root x, right, and into f dash of x, and that would be negative 2x. Okay, into cos x. Now this negative sign that you see here, negative sign, this is outside the bracket. Okay, so by product rule, we have a plus sign here. Okay, we'll have a plus sign, but because outside we have a negative sign, let's put negative sign there. Okay, now first function will remain as it is. Okay, first function will remain as it is, and the derivative of second function needs to be computed. That is negative sin x. Okay, negative sin x. So we've got something. Okay, we've got something which now we can take care of. Okay, look, let's cancel 2. Okay, let us cancel this 2. Negative into negative, so we do have a positive term there, positive sign, and we will have x cos x in the numerator and 6x in the denominator, right? Minus, let's keep this root 1 minus x squared as it is. This negative sin x is there, so let's make it positive. Let's make it positive, and then we have our famous limit sin x upon x. Let's not forget that it is actually 6x, but sin x upon x, that limit is 1. Okay, so at the end, what are we getting? X will get cancelled, cos 0 is 1, so this is 1 upon 6. Sorry. Yeah, so that is 1 upon 6 plus this is 1 into 1 upon 6. 1 upon 6 plus 1 upon 6 is how much? 2 by 6 or 1 upon 3. Okay, the answer is 1 upon 3. That is option B. Okay, that is option B. Now, can we solve it on calculator? The answer is, of course we can. Let's do it. Okay. Now, I have been told by students that in NEST, the calculator as you have it for IIT is not there. It is only the basic calculator. Am I right? I mean, the TCS calculator, the big one with all the inverse and sine functions, it's not there for NEST, right? Yeah, they have that smaller version of the calc. But anyways, assuming that it is an IIT question, we can solve it on calci. Okay, x tends to 0, and both inverse trigonometric function and trigonometric function results. I have changed my calculator's mode to radian. Let's take our x value as 0.001. Okay, let's take our x value as 0.001. Let's now see. First of all, I have to take sine inverse of that minus sine of that, and I have to divide it by the cube of the answer. So answer isn't the number that we stored earlier. What did we get? Point and so many 3's. So that clearly indicates that our answer is 1 upon 3. So any doubt in this problem? What have we done? We have applied the L-Hospital's rule 2 times. Okay, and we have also made an adjustment in between. You can also try doing it without adjustment. If you manage to get the answer quicker than this, you go for that method. But in the exam, such things will happen. You have to take quick decisions, you have to make quick decisions to arrive at the final answer. Okay? And the moment you realize that the sum is doable, I think you should go for it. Even if it takes half a minute extra, that's fine. Any doubt? Understood? Okay. Cool. So that was our first question. Now also listed down the year there. Let's go to the second one. Okay, let's go to the second one. This came in 2008. Okay, this has come in 2008. Our second question. The limit of the function f of theta equal to 1 minus cos of m theta upon 1 minus cos of n theta, both m and not 0, as theta tends to 0 is n squared upon m squared 1, 0, m squared upon n squared. Now this should be doable, right? It's pretty simple. Theta is tending to 0, m theta will also tend to 0, n theta will also tend to 0, cos 0 is 1. So that is already in the 0 by 0 form or indeterminate. Okay, apply the rule. Okay, what does L-Hospital give us? Okay, you can also do it by that adjustment thing. Okay, I'll tell you it later. So if we apply the rule, what are we going to get? Derivative of 1 is 0, derivative of cos is negative sign, so that will make it positive. So it's sine of m theta into m and in the denominator it is sine of n theta into n. Correct? That's pretty straightforward. Now, if it is giving us 0 by 0 and if differentiation is easy, please go for a hospital again. Okay? Go for the rule again whenever possible. Okay? It's giving 0 by 0 because sine of theta and that's true. So this is cos of m theta into m squared upon cos of n theta into n squared. That's not in the 0 by 0 form, substitution works. Cos 0 is 1, so that's m squared upon n squared, option D. Have you understood this? Yes, see, alternately what you may have done is this. Okay, let me write it here. You would use the formula limit as theta tends to 0, 1 minus cos theta upon theta squared equal to half. Okay, you would have done that also. And to do it, basically what you would do is you would divide the numerator by m squared theta squared and you would divide the denominator by n squared theta squared. Okay, let me do it. Let me do it here. Yeah, okay. Look. For the division of division of numerator and denominator by theta squared, it shouldn't be a problem, right? 1 minus cos n theta upon theta squared divided by 1 minus cos n theta again by theta squared. So, well, that is now squared up. But for this m squared part, you are dividing it, and here you are dividing the denominator by that. So essentially what are you doing? You are basically multiplying this box bracket by the term m squared by n squared, and that's the same answer that we've got, right? Both the limits there would be 1 by 2. Okay, both the limits would be 1 by 2 and this factor remains, and hence the answer is m squared by n squared. Got it? Yes? Yeah, okay. Yes. And can we do it here? Can we do it here? Yes, we can do it. Let's okay, I think it's pretty straightforward, so let's not choose any theta. 1 minus cos of let's choose m as 5.001 upon 1 minus cos of let's choose this as 2. Okay, n as 2. So it is very close to 6.25. Okay, and 25 upon 4 is actually that. Okay, so whenever it is a limit problem or whenever limits are involved, always think of using a calculator in whichever mode you have. Okay, cool. Question 2 is done. Let's go to question 3. This is from 2009. Question number 3. The limit of the expression x tending to 0 sine of x squared pi by 2 upon sine of 5x by 2 the whole squared is, okay, let me write it here. It's a bit small font. Limit x tends to 0. There are two functions here. The numerator is sine of pi x squared by 2. So pi by 2 is there, and then we are squaring x only. And in the denominator it is sine squared actually of pi x by 2. Okay, sine squared pi x by 2. Okay, that is what we have now. And well, in almost every case it will be in 0 by 0 form, and even here you see it is already in the 0 by 0 form, right? Sine 0 0 sine 0 0. Okay, so can we apply the L'Hospital's rule there? Can we do it? Yes, we can apply L'Hospital's rule here. Okay, let's do it. Okay, first go for the numerator. It is cos of pi x squared pi 2 into chain rule derivative of inner function pi by 2 as it is into 2x. Okay, come to the denominator. In the denominator we have got sine squared, isn't it? Sine squared, so it will be 2 sine pi x by 2. Okay, 2 sine pi x by 2 into cos pi x by 2, because first we have taken the derivative of squared. So now the inner function is sine, its derivative is cos, and then this should be multiplied by derivative of pi x by 2, which is pi by 2. Okay, now pi by 2 goes, 2 they also go, and I am now recommending you not to apply the rule again. Okay, not to apply the rule again, but take out the terms which do not give you 0. Pi x squared by 2 is one of them, the other one is pi x by 2. Oh wait, is it giving a 0? Oh, okay, sorry, it is giving, oh no, sorry, it's not that. Sorry, I got confused because of pi by 2, but x is tending to 0. Okay, so that won't be a problem. Okay, now what is left? In the numerator x is remaining, and in the denominator sine of pi x by 2 is remaining. Okay, I think I'm not missing anything here. Cos of pi x squared by 2 is there, cos pi x by 2 covered, x covered, sine pi x by 2. Okay, good. Now, do you agree that the first term here will be 1? Cos of 0, 1, cos of 0, 1. Yes, that is going to be 1. And look now, for the second one, I will write 1 in the numerator. Okay, and I will send that x in the denominator. So it will go in its denominator, and because this has pi x by 2 there, okay, let me divide this by pi by 2. Okay, and then let me multiply this by pi by 2. Okay, so this limit becomes 1, this limit becomes 1. Okay, and that is pi by 2 in the denominator, so eventually it will come in the numerator and become 2 by pi. Okay, 2 by pi, that is option C. That is option C. And if you are not convinced how we did that, if you are not convinced, fine, so we can apply the L'Hospital's rule right here also. Okay, so see, this is our step, then here we have made that adjustment, or what can we do? We can say, let us differentiate that again. Derivative of x is 1, derivative of sine is cos, and then derivative of inner function, so that eventually again will give you 2 by pi. Got it? 2 by pi. Yes, so the answer in decimal form should be somewhere close to 0.6, right? Somewhere close to 0.6. So you can do it on calculator, but let's do it on Desmos this time, because that square part is a bit difficult to enter in my calculator. Okay, so what is the function? Sine squared in the denominator. Okay, sine squared pi x by 2 in the denominator, and in the numerator we have got sine of pi x squared by 2. Okay, so this is the graph. It's a pretty decent looking curve, and okay, fine. Look, we are only interested near 0. See, at 0 it should show as undefined. See, look, at 0 it is showing undefined. Okay, and if I draw a horizontal line, y equal to 2 by pi, that appears to be a tangent to that curve, but it is not, because the function is not defined there, but it matches. It's 2 by pi. Okay? Okay, by looking at this graph, can you tell me whether our function is odd or even? Yes? By looking at this graph, can you tell me whether this function is odd? It is an even function. Look here. For sine squared, you are convinced that it will be an even function because, well, even odd into odd is even. But take a look at the function in the numerator. Sine of pi x squared by 2. Sine is odd. But what about x squared? It is even. That would make it even function. So even if we just plot the numerators graph, okay, even if we just plot the numerators graph, that would still be symmetric about y-axis. Albeit a non-periodic function, that is still even. Okay, that's the way. Okay, cool. So no doubt in question 3, right? You have understood it. Yes. Yeah, so these problems that I found, they are very much patterned, at least for the first 3 years, 7, 8 and 9. And then I found this one in 2010. Okay, in 2010 this problem came. Okay, fine. This is our question 4. It says limit as x tends to 0, 1 upon x squared into definite integral from 0 to x t upon t raised to 4 plus 1 dt. Okay, now there could be two ways to solve this problem. First, by evaluating the definite integral, and second, without evaluating the definite integral. Any way you can choose. And suppose we wished to solve this problem by evaluating the integral first. Well, I'm not going to do that, but I will give you that as homework. Okay, so how will you evaluate the integral? Can you tell me, please? Will you evaluate the integral? You will choose the substitution t squared equal to u. Why t squared equal to u? Because the derivative of t squared in its variable form is available there, right? So t dt would be half du. Is it clear? T dt would be half du. Yes, and then what would be the limits? Okay, sorry, not x, t and u. T0, u0, and if t is, sorry, t0, u0 there. And if t is x, what would be the limit on u? It would be x squared. Okay, it would be x squared, and then I think its integral will be something tan inverse. So you can go for it. Okay, so I'll leave this part to you. I'm going to choose the other method, which is not evaluating. So then how are we going to solve it? Okay, the integral, okay, by not evaluating the integral. So let's think about it now, like what can we do to solve that particular problem without using the evaluation or the value of the integral. Look, at the end of the day, it is a limit problem. Okay, with 1 upon x squared sitting outside the integration, that is a clear indicator that we should be going for L'Hospital's rule, if at all it applies, right? And if we choose 0 here, then we'll get 0 there, but also that will make the limits on the definite integral same. Okay, that will make the limits on the definite integral same, and therefore it will be in the 0 by 0 form, and therefore L'Hospital's rule is applicable. Okay, so tell me now, if we apply the L'Hospital's rule, there is no question of the regarding the derivative of the denominator, that is 2x, isn't it? That is 2x. How will you now go for the derivative of the integral? Remember, I told you a rule which we called DUIS, differentiation under the integral sign, or we also call it Leibniz rule sometimes. And what do we exactly do there? First, what do we do is we keep the limits and this part as it is, and we take the partial derivative of this with respect to not t but with respect to x, okay, because we are differentiating with respect to x, and because there is no term in x in that function, I will write it as 0. Then what next? What follows is we put the upper limit there. What do? We put the upper limit there and we multiply this by the derivative of the upper limit with respect to whatever variable we are differentiating it with respect to, right? So that's x, so derivative of x with respect to x is 1, okay. Then we go to the lower limit, we substitute it in the integrand. Anyway we are getting 0, but we again multiplied by the derivative of the lower limit with respect to x, so that's 0, okay. Have you understood till this? If you see any other solution, they would directly go for this, okay, without clarifying how did that come. But that is actually the differentiation under the integral sign. The first term is the partial derivative of the function of t with respect to x. For x, t is a constant. So that's it. Okay. Okay. So what is the good news now? The good news is x will get cancelled. You've got this 2x here. We've got this x here. Okay. And x raised to 4 plus 1 will come in the denominator. X will go. And the final answer is 1 by 2. 1 by 2 is option C. Okay. The option does not exist. That might lead to some confusion, because if we see all numbers as all 4 options, then we know that the limit exists, so anyhow that rule will be applicable. Fortunately for this case, we were not required to argue anything about with the applicability of the L'Hospital's rule. One reason is the function t upon t raised to 4 plus 1, that is a good function in the sense it never becomes undefined, okay, nowhere near 0, or rather throughout its domain it never becomes 0, like, because it has t raised to 4 plus 1 in the denominator. So as far as the applicability of the rule is concerned, we know it's very well behaved, okay. And secondly, although x is tending to 0, we have x squared there in the denominator, okay, we've got x squared here, which again says no matter from which direction we have that x approaching 0, x squared will always go to 0. Okay. Okay. Now let's verify it now on Desmos. It also does all that stuff also. Okay, so how to verify that? Look. What can we do is we can go for 1 upon x squared first into integral from 0 to x, okay, t upon t to the power 4 plus 1 dt. Okay, so this is how the function is, right? This is how the graph of the function looks like. And we have got our value as 1 by 2. Let's see if it is there. Clearly it's 1 by 2 because this is rounding it off. But at 0 we should get it undefined. Okay, yeah, see, look. At 0 we got undefined, but near that, everywhere it is 0.5. So see, at point 2 it's not 0.5. This calculator is rounding it off to 0.5. Okay? Okay, so you can also use Desmos to evaluate integrals. It's a good tool to have. So, any doubt in that problem? Or shall I explain it again, or you have understood it? Will you be able to solve this same problem using the evaluation of integral? Okay, good. Alright then, let's move on. That was our 4th one. Let's go to 5th. Okay, let's go to 5th. this came in 2010. Okay, let the function f of x be minimum of the functions x comma x squared where x belongs to R. The function fx is continuous everywhere, continuous except 0 and 1, differentiable everywhere except 0 and 1. Now look, what two functions do we have? We have y equal to x, y equal to x squared. Correct? Y equal to x, y equal to x squared. And we know that y equal to x squared is always greater than or equal to 0. But not y equal to x. Now when they say minimum, we have now understood that for negative values of x, okay, for all negative values of x, it's not y equal to x squared that is going to be the function's definition, it's rather y equal to x. Correct? It's y equal to x because that's negative. And suppose this is that 1 comma 1 point where both the curves meet in the first quadrant. This is also y equal to x. Now why did I not draw this particular portion of it? I could have drawn it. But I know when it comes to y equal to x squared, and I think I have told you this many times, that when n is greater than 1, then x always remains greater than x raised to n for all values of x in between 0 and 1. Okay, for all values of x in the open interval 0 and 1. So be it x cube, x squared, x raised to 1.1, all of them will be below that. Okay, so this will be the parabola. Well, we can draw the symmetry by symmetry this portion also, but what will be the function's representation? The function's representation would be this line followed by this and then followed by this. Okay, now there is no doubt that this is continuous everywhere. Okay, this is continuous everywhere, so option A is right. Okay, I think this is a multiple select question. Now, is it differentiable everywhere? It's not differentiable everywhere. It is differentiable everywhere except two locations. Which two locations can we see now from the graph? X equal to 0. What is the right hand derivative? Right hand derivative is 2x at 0. That is 0. But what is the left hand derivative? It's a line, derivative of line. Well, y equal to x is constant, so that's 1. Unequal, so it's not differentiable at 0, and from the options we can easily conclude that it's also not differentiable at 1. Why is it not differentiable at 1? Again same logic. Look, at this point where x is 1, what is the left hand derivative? It is 2x at 1. That's 2. But what is the right hand derivative? 1. Are they equal? No, they are not equal. So it's not differentiable at 0 and 1. Everywhere else it is differentiable. Okay. Raise your hands if you have understood question 5. Right? And such questions can come in your IISc or even future nests also, because it will test everything. Graphs of functions, behavior of functions, limits, continuity, differentiability, everything. Okay, in some cases also periodicity. Okay? Okay, question 5 is done. Let us go to question 6. Question 6. Well, this is from 2015. Okay, this is from 2015. Suppose a limit as x tends to infinity, x squared plus 1 upon x plus 1 minus ax minus b is 0. Then a cube minus b squared is negative 1, 0, 1 and not determinable. Okay, now Not determinable could also be an option here, because it may appear to us that we have only one equation at our disposal and we have got two unknowns, a cube and rather a and b basically. Okay, but don't mark it, because unless we solve it, we will never come to know. Okay, yeah. Now, one key point which you should take away is limit is existent. Limit exists, which means if by some means we could write it in one polynomial by other polynomial form, we can apply the rule, right? So let's go for it. Let's take the denominator here, x plus 1, x squared plus 1 will remain. Now we have to multiply negative ax minus b by x plus 1. So minus ax squared minus bx minus ax minus b. Okay, and this is 0. So far we have not done anything. Okay, we have just brought that ax b thing in numerator. Now observe, degree of denominator 1, degree of numerator 2. Now this contradicts with the existence of limit, because we clearly know if x is tending to infinity and we have got a rational function with numerator's degree greater than that of the denominator, then the limit cannot exist, like, or we write infinity there or negative infinity, but definitely not finite. But here the limit exists and is finite. Limit exists and is finite. Therefore, what we must conclude? Therefore, degree of numerator must be 1. Same as that of denominator. Okay? And therefore, 1 minus a is 0 and therefore a is 1. How did we get that? How did we get that? Look, x squared is here, minus a squared is there, minus ax squared is there. Coefficient of x squared should be 0 because degree of the numerator must be 1. Therefore, a is 1. Okay, but that's only half of the problem. Now you have understood that because we have determined a and we still have to continue solving the problem, option D may not be the right. Sorry, option D may not be the right option. Okay, option D may not be the right option. Therefore, we get, what do we get? Limit x tends to infinity 1 minus px minus x, now I can write because a is 1, minus p upon x plus. Now can we apply the L'Hospital's rule? We can, because it is definitely in infinity by infinity form. Could be negative infinity, but that hardly matters. Okay, so what does L'Hospital give? To it, denominator is 1, 0, minus p, okay, minus p minus 1. Okay, don't write this b because it is a constant, so its derivative is 0. Okay, so what have we got? Negative b minus 1 is 0, so b should be negative 1. We've got b as well. So what will a cube minus b squared be? A cube 1, b squared 1. A cube minus b squared is 0. Okay. Have you understood this, or got it right? Okay, cool. So see, look, because the limit exists, we can conclude that the numerator's degree has to be equal to that of the denominator. Can't even be less than that. Or can it be less than that? It could be less than that, but in that case, okay, let's just consider that possibility, although I don't think the problem setter intends to do that, but let's quickly go for it. Okay, because anyhow the limit is 0. What if, suppose, what if the degree of numerator were 0? Okay, what if the degree of it, because see, that is a perfectly reasonable assumption. Why is it perfectly reasonable? Because look, x is tending to infinity and denominator is x plus 1, so denominator is anyhow an extremely large number. So if we have a numerator of the kind which has just a constant term, that would still mean that the limit is 0. So let's go for it. A's value won't be different. A's value would still be 1, right? But what about b? Okay, a plus b in that case should be 0, but that will also give us b as negative 1. Have you understood this? What did I do? I went for the coefficients of x now, okay, which are negative b and negative a. If we take the negatives one outside, we get a plus b. We don't want the numerator to be of first degree, we want it to be a constant polynomial, basically a constant. So a plus b should be 0, that again gives us b as negative 1, essentially the same result that we got here. Correct? So even if we consider the other possibility, we still get the same answer. Okay? So yeah, that's question 6 for you. Okay? No problem, right? Everybody has understood? Yeah. Okay. Alright, next one. Question 7. Question number 7. This is from 2015 again. Yeah, okay, this is also from 2015. Let R be the set of all real numbers and let f be a function defined from R to R. Let it be a differentiable function satisfying f dash of x equal to x plus f of x. If the graph of f of x passes through the origin, then limit as x tends to 0, f of x upon x squared does not exist. 0, 1 upon 2, 1. Okay. So a function is defined and its domain is the set of all real numbers. Okay, it is differentiable. It satisfies this differential equation. So that could be one way of solving the problem. It's a linear one, you see. This differential equation is a linear differential equation. If you call f of x as y, f dash of x will be dy by dx, dash for y and x. Okay, so what can you do here? In usual form, this is p and this is q, and this is very much solvable. Okay, and additionally they've also given us if the graph of the function passes through origin, that means y of 0 is 0. That is an additional piece of information. So we can actually find the particular solution of this differential equation because it is linear. Okay, I will leave that part to you. I will leave that part to you. You people know the general solutions. Y into e raised to integral p dx equal to integral of q into e raised to integral p dx plus c. Okay, that big expression. But what we will now try to do is we'll try to solve the problem without solving for y or f of x. Okay, look, do you think that L'Hospital is applicable here? It is. Why? Because denominator is 0, numerator is f of 0, the graph passes through origin, so this must be 0. So let's apply the rule. What will we get on application of L'Hospital's rule? Denominator 2x, numerator f dash of x. Now what to do, because we don't know f of x, but we have that expression for f dash of x, which is x plus f of x. Therefore, we get limit x tends to 0 x plus f of x upon 2x. Now, is it still in the 0 by 0 form? It is 0 plus f of 0 upon 2 into 0. That is still in the 0 by 0 form because it passes through origin and all that stuff. Let's again apply the rule. Let us again apply the rule. Okay, let us again apply the rule. Derivative of denominator is 2. Derivative of numerator is 1 plus f dash of x. What is again f dash of x? X plus f of x. And you have got the answer, that's 1 by 2. Because x is 0, f of 0 is also 0, so answer is 1 by 2, option C. Raise your hands if you have understood question 7. Got it, right? Okay. Can you solve the differential equation as homework? Yes, you have to. Okay, cool. Question 7 is done. Let's take one more. Let's see how many of them I have. Okay, maybe we can do the rest tomorrow with few more. Okay, this is our question number 8. This is our question number 8. This came in 2016. Let a function f from closed interval 0 to infinity to r be defined as follows. F of x is equal to mod of x minus a minus 1 when 0 is less than or equal to x less than 2, and it is b into x minus 2 squared, x is greater than or equal to 2, where a and b are real numbers with a belonging to open interval 0 to 2 and b not equal to 0, then there is exactly one value of a which makes f a continuous function. The continuity of f depends on the values of both a and b. F is continuous if and only if a plus b is 1. F is not differentiable at exactly one point in its domain. Acha, so we have got that function whose domain is closed interval 0 to infinity, so 0 is there. And okay, look, whatever may be the value of a, mod x minus a minus 1, we can definitely come up with 2 points. First, it is continuous everywhere. Okay. Is it differentiable everywhere? No. Where will it not be differentiable? Any guesses? At x equal to it won't be differentiable because it will have a corner there. Okay, not differentiable at x equal to a. How about the function b into x minus 2 square? That's a polynomial function. So without any hesitation, we can say that it is continuous and differentiable. It is continuous as well as differentiable. So when it comes to checking for continuity of the piecewise defined function to us, the only point of investigation has to be 2. Okay, so let's go for it now. But you have to write it. Therefore, we only look at x equal to 2. That is where the definition changes. Okay? That is where the definition changes. Let's find left hand limit. Which definition will be applicable? Mod over definition will be applicable. right? So it's mod of 2 minus a minus 1, and because a is less than 2, 2 minus a will be positive, so that will be 1 minus a. Now please understand this step. Okay, please understand why is the limit of mod x minus a is 2 minus a. You may ask, a is also less than 2, x is also less than 2, how is that possible? Look, a is static, it's not going to move. So because a cannot be equal to 2, I can always have many numbers, or as many numbers as I want, between a and 2. And our x is a dynamic variable, you can say it is approaching. Okay, it's not static like a. So x will eventually cross a and will continue its journey towards 2 from left. That is why mod of 2 minus a remains positive. Have you understood this argument? Okay, that is required. That understanding is required to continue. But it is to believe that what we are doing is correct. Okay, so that is LHL. How about RHL? I think RHL is pretty straightforward, because all we have to do is just substitute, right? All we have to do is just substitute. So 2 minus 2 0, so that is 0. Okay, now for continuity, by the way, this also happens to be f of 2. 1 minus a should be 0, so a should be 1. So value of b doesn't decide continuity. For continuity, a is equal to 1. Okay, a is equal to 1. So option A is right. There is exactly one value of a which makes f a continuous function. And as far as I remember, this is not a multiple select question, so option A is correct. But let's also check for the differentiability. Okay, clearly B is ruled out. Continuity of f depends on both A and B. No, it doesn't depend on B. Right, it doesn't depend on B. Now, look, so that also rules out option C. We only want A to be equal to 1. B can be anything. Okay, and well, furthermore, they are saying B is not equal to 0. Okay, so C is also ruled out. So let's go to D now. F is not differentiable at exactly one point in its domain. We have already found out that point. Not differentiable at x equal to. So this is first point of discontinuity, or function being, sorry, not differentiable, not discontinuity, function being not differentiable. Okay, so x equal to a, not differentiable. Oh wait, my net went. Can you still hear me? Yes. Okay, just a second, because on my mobile I don't see my screen. Wait. Anyways, okay, let's continue. At x equal to, it's not differentiable, right? At x equal to, it's not differentiable. Now, okay, which other point should we look for? We should look for 2, because we know continuity is necessary for differentiability but never sufficient. Okay, so let's go for it now. Right hand derivative. Okay, at x equal to 2, what is the right hand derivative? B into 2 into x minus 2, because x squared derivative is 2x. That is 0. Left hand derivative at x equal to 2. What's the function there? From left, it is mod x minus a, and we know that eventually it will surpass, so we can say it is only mod, it is x minus a minus 1. Okay, derivative of x minus a minus 1 at 2, that is 1. Right, derivative, and again these are not equal, so also not differentiable at, also not differentiable at x equal to 2. Okay, so there are 2 points, not exactly 1 point. F is not differentiable at exactly 2 points in its domain, so D is also not. Well, anyway, in the exam you will come to know whether it is a multiple choice question or multiple select question. So once you get the correct option, you're pretty much done with that particular question. Now one last part is remaining. We would like to see how this looks on graph. Okay, mod x minus a minus 1. Mod x minus a minus 1, and we want this only in between 0 to 2, and a, let's keep a between 0 and 2. Okay, so that is how the graph is going to look. Okay, and it is b into x minus 2 square for x greater than or equal to 2. Okay, now look, as we change a, okay, the function will be discontinuous, but only when a becomes equal to 1, it kind of joins the bottom of that red curve, which is x minus 2 square into b, right? But the square of the slope of x minus 2 squared into b is 0 there, and this is a mod function, so its slope can never be 0, and it is independent of the value of b. Okay, it is independent of the value of b, and you may think that the slope will eventually become 1. No, it's not. At 2 it will never become 1. It is always going to be 0, no matter what value of b you take. Okay, so we have successfully verified our result graphically. Alright, we have solved around 8 problems today, and my plan is to solve, there are a few more problems from limits. Those problems we will solve, so that should be the end of limits. Okay.